Well, thank you very much, and I want to thank Margaret and the program committee for inviting me to participate. This has been an exciting meeting. It's fun to come someplace where people really know all these terms and are engaging in a fairly high-level discussion of what's going on. I'm going to be talking about more theory than models, so at least for the most of what I have to say is model-free. It doesn't depend on which model you're going to be using. However, I'm going to use a lot of symbols, and not to scare you away, especially at this late hour, and I want to thank you all for staying, that the symbols I'm going to use, I've tried to make them so that they have some meaning. And I'm going to focus on outcomes. Okay, we've been talking about outcome measures, but we haven't yet talked about how do we use this to measure outcomes, the effects of what we're doing. And so I want to look at it more from a theoretical point of view of what these models have to do and how you have to interpret them when you're measuring outcomes. Okay, my financial disclosures, I don't have any financial interests, unfortunately. And my other interests I'm disclosing is that I'm a low-paid employee for the Food and Drug Administration on occasion to be a reviewer, and the research that I'll be describing as part of my talk is supported by the National Eye Institute. Okay, in measuring clinical outcomes of behavioral and symptom-targeted interventions, we have to we're looking at changing aspects of patients' behavior, feelings, symptoms, or daily functioning. And in these cases, the treatment is goal-directed and targets specific problems that are experienced by the patient. And the goals of treatment are highly individualized to meet each patient's personal priorities and to be feasible given each patient's capabilities. So the question is, how does one measure outcomes when the treatment is customized to each patient? Okay, so we need an outcome measure that recognizes and accommodates treatment plans targeted to the multiple personal goals of intervention and different capabilities of individual patients and clients. The Goal Attainment Scale, or GAS, which makes for a number of very clever slides, first developed in the late 1960s by Thomas Kurosuk, who's a clinical psychologist, and his mathematician, Robert Sherman, to serve this need. And I understand these slides will be on the website, so you'll be able to get the references off that later. Okay, goal attainment scaling, the way it's implemented basically is that at baseline, during the evaluation, the clinician sets goals for the patient and then rates how far the patient is from the goal. The goal would be at the origin of the scale, be at 0, and a rating might be they have at the baseline, in which case they'd get a rating of 0, or they're at the goal at baseline, or they have some ability, in which case they'd be given a score of -1, or they have no ability, things are as bad as they could be, given a score of -2. Okay, upon follow-up, then they ask, was the goal achieved? And if it was, then the rate above 0, it could be 0 if it's at the goal, it could be above 0 if they did a little bit better than expected, and it would be +2 if they did a lot better than expected, or they could lose ground, the goal wasn't achieved, but they maybe made progress. So it could be get closer to the goal but not achieve it, and be ratings accordingly. So these are just ordinal ratings that are assigned to distance from the goal. It's done on a goal-by-goal basis. Okay, I'll have more to say about the specifics of the scoring of that later in the talk, but GAS relies on therapist ratings, which necessarily incorporate therapist-specific biases. Okay, and the outcomes are scaled relative to the choice of goals in the rehabilitation plan. Rating of 0 means the patient's at the goal, but not all goals are the same, so the meaning of the scale changes across goals. 0 doesn't mean the same thing for every goal. So we need a theory that explicitly identifies all the relevant variables and then can be reduced to a valid measurement model. Okay, so what I'm going to tell you about first is kind of an overview of how to model outcome measurements from rating scale responses. And remember, this is a theoretical approach, not a specific model. The specific model comes later. And we'll start with, to make it a little easier rather than using gas, we'll start with patient self-report, the type of questionnaires we've been talking about through the meeting. Okay, I then want to get into the question of intervention-specific differential item functioning. And we're going to be modeling the effects of interventions that target item difficulty. In other words, if you're treating symptoms, that you may change some of the items and have no effect on other items. And I'll give some examples of intervention-specific diff from my field, low vision rehabilitation. And then we'll finish with a critical analysis of goal attainment scaling and show a new approach to how we might implement this GAS strategy. Okay, so just to remind you, patient reported measures in a form of a functional ability questionnaire. In my field, visual function measures, we use one of the instruments that's popular is the VF14. They're simply 14 items that describe everyday activities. The patient assigns a rating of no difficulty up through unable to do, and then has the option of saying not applicable, which is treated as missing data. Okay, so when we're going to measure functional ability is a latent variable, and it's a trait of the person. So you could substitute your own latent variable in for this. I'm going to use functional ability just so we have something substantive to talk about, but use whatever term you like for this latent variable. Okay, I want to introduce the terminology I'm going to use. Each person has some level of this functional ability, and we're going to use a generic term person measure to refer to that, and we'll use the symbol P to represent person measure and subscript N for a specific person N. Okay, each activity requires some level of functional ability to be performed with these, and we'll call that the item measure. And we'll use the symbol I for item measure, subscripted J for item J, just the index for the item. We're going to introduce a concept of functional reserve, and which is simply the difference between the person's functional ability and the ability required by the activity. So the person measure tells you how much you have. The item measure tells you how much you need in order to endorse the item. Functional reserve, or some other term if we're not talking about function, is simply the difference between the person measure and the item measure. And I'm using the symbol R for reserve, and it's subscripted both for the person and for the item, which is just the difference between P and I. Okay, now what we're asking the person to do is judge the difficulty of performing an activity. And our expectation is that their perception of the difficulty of performing the activity is going to depend on the functional reserve. So in other words, if the person has far more ability than is required to perform the activity, they should tell you it's easy to do. On the other hand, if the amount of ability they have is less than what is required to do, there's a high probability they're going to tell you. Sorry, there's a high probability they're going to tell you they can't do it. Considering those extremes, everything in between, as the amount of functional reserve changes, you would expect that the estimate of how much difficulty it's going to take will vary with functional reserve. And then to respond with a particular rating category, and we'll use X to indicate which ordinal rating category we're responding with, functional reserve has to fall in an interval that's defined by the patient. So the criterion, or the category threshold, which is symbolized by C, capital C, the functional reserve has to be greater than the category threshold to respond with category X, but it has to be less than the category threshold to respond with that category X plus 1. Okay, so C then is just a criterion that is set for that response category. But the problem here is that P, I, and C, the person measure, item measure, and category threshold, are all fixed variables. It's a completely deterministic measurement. Now, we can probably agree that functional ability is a fixed property of the person, but what we're saying here is the required functional ability is a fixed property of the item, which may not be true, and that the response threshold, C, is a fixed property of the interval, which most certainly is not true. But in the real world, these variables are inferred from the observations, and there's uncertainty about the inferred values. Okay, so if you have a measurement theory or measurement model that's worth its salt, it ought to be able to explain physical measurements. So we'll use as a metaphor a balance scale. So the trait of the person, in this case weight, but it can be any other trait, functional ability, is being compared to the trait of the item, which is the same thing, in this case weight, but it would be something else. And we're simply dichotomously scoring each comparison. We're going to compare the person to every item, and we'll score it a 1 if the person's heavier than the item. We'll score it a 0 if the item's heavier than the person. That would be a dichotomous scoring system. But if we want to do a polytomous scoring system, we need another set of weights. In this case, we'll call the categories. So for each item, you would put for example, category 1 weight in with the item, and we find that the person's heavier than that combination of the item plus the category, so we'd give it a 1. We'd put category 2 in. In this case, in this example, the item weight plus the category weight are heavier than the person, so we give it a 0. Because we know those category weights are rank ordered by weight, all the rest of them have to be 0, since they're heavier than the one that got us 0. So we give them all 0. We add up those dichotomous scores. In this case, we get a 1, but that's the polytomous score, would be the response for each of those categories. So for measurement theory, the kind we're using, Pn is a fixed trait of the person. But each person is going to interpret the item. Okay, so like in my field, if we ask how difficult is it to read, one person's thinking, well, I'm sitting at home with my 100-watt bulb in my lamp reading the USA Today. Another person, we ask that same question about reading a newspaper, they might say, I'm sitting at home with my 40-watt bulb in my lamp trying to read the Wall Street Journal or the New York Times, and it might be different tasks. But the question isn't specific enough, so it allows for individual variations in the interpretation of I. So we can make I, the item measure, is really going to be indexed to the person in addition to being indexed to the item. The fixed variable ij can be interpreted as the average I across your population that you're interested in studying. So in my case, it would be the population of visually impaired patients. In your case, it would be a different population. But how that variable, the average value of that variable, is the fixed variable that we're trying to estimate. We then can define a random variable, which we'll just use E for error. And that random variable is the difference between the I for the person and the average I for the population. Okay, so, and we expect this to vary both across people randomly and across items. Similarly, each person creates their own categories. And so the category thresholds would be subscripted for the person. So category threshold for X would be CNX, and that's person N's response criterion for using rating category X. And CX, which is a fixed variable, would be the expected response criterion for response category X for your population. In other words, it's the average value of C and X across all people. And then we would have an error term associated with that. Again, we'll use E, but we'll subscript it NX, and that's just the difference between the person's category threshold for category X and the average for the population. Now, person N is using difficulty ratings to estimate the magnitude of their own functional reserve for a given item. And so in this case now, functional reserve would be the difference between the person measure, fixed variable, the average item measure, another fixed variable, and the error term that goes there. So to respond with rating category X, functional reserve has to be greater than the threshold for X and less than the threshold for X plus 1. So now we put in fixed category thresholds, which are the average for the population, CX and CX plus 1, And there are errors associated with those category thresholds, which get added. And then we still have the error for the fixed variables on person measure minus the item measure. So this describes the conditions that have to be satisfied in order for the person to use response category X given the assumptions we've made up to this point. Just as a side note, two-parameter item response, or the graded response model that a lot of people use in item response theory, assumes that the error term on C, E and X, is 0 for all values of n and all values of x. They don't make that assumption explicitly. You just have to assume that in order to derive the graded response model. Okay, back to the story. Okay, so to respond with rating category X, functional reserve has to be greater than one threshold and less than the other threshold. So what we can do here is define a new random term. I don't have a pointer, but simply what we're going to do is take E and J and add it to every term. All right, and so we'll create a new random variable called E and JX, which is just the sum of the two random variables we've defined. And now we can write the measurement scaling theory just in terms of the two fixed variables, Pn and Ij, where Ij is the average, and the average category thresholds for the population, Cx and Cx plus 1, and then a random variable for each of those. Okay, so that's the theory. All the Roche, IRT, confirmatory factor analysis, all the stuff you're doing starts here. And every one of those things can be derived from this simple equation simply by making specific assumptions about the distribution of the random errors. And the theories differ from one another based on the kinds of assumptions that are made about those distributions. I mean, the models differ from one another. Roche theory, in particular, all Roche models, what they have in common is they assume that those random variables are independent of each other, no matter what the indices are. Okay, so how do we add that to our balance scale model? Well, we need a random error generator. So we'll just put air puffs on the pans that are generated by a complex system that has a computer that controls how much force is going onto the platform and which of the two pans is that's getting the blast of air. And as you can see in the computer display, it's a normal distribution we're choosing from. On each trial, we randomly so I'll keep doing that. Randomly draw a force from that distribution. Its average force is 0, and it's either positive or negative, and then we blast one of the two pans. That gives us our error. If we blast the item pan, it makes the item look like it's heavier. If it blasts the person pan, it makes the item look like it's lighter. Okay, so let's go back to our VF14. Just to remind you of the real world, the tasks that we're actually performing is asking the patient to rate the difficulty of performing each of these activities. Okay, these are some actual data from the VF14, and it's taken from an Excel file. Look at the colored matrix on the left side first. Each column is one of the 14 items. Each row is one of 200 patients, visually impaired patients, who responded to the questionnaire. And the colors correspond to the response they gave to that, each person gave to that item. Okay, so if it's blue, they said it was no difficulty. Up through red, unable to do, and if it's white, that means it's missing. They said it was not applicable. You can see a banding pattern in the data because what I've done is I've summed all the rank scores for the responses for each column across all the patients. And that's the raw score for each item. And then I ordered the items by their raw scores. And then I summed across all items for each patient to get a patient raw score, and I ordered the patients by their raw scores. So when we do that, if in fact we're making a measurement, we should get what's called a Gutman scale. And a Gutman scale would produce this banding pattern, that once you go from blue to green, you don't go back to blue again. You can only stay green or go to yellow. And then when you get to yellow, you can't go back to green or blue. You have to go to the next step or stay the same to orange as you move across or move down. Okay. What these measurement models do, once you make some assumption about the error, measurement models then use maximum likelihood estimations techniques to estimate a person measure for each person, an item measure for each item, and a category threshold for each of these response categories in order to produce a Gutman scale, the most likely Gutman scale. And that's what's generated on the right side of that figure, or right matrix, is the estimated responses by this group of patients to these 14 items, based on the data themselves. Pardon? Guttman, Gutman, Louis Gutman. It was a paper back in the 1940s, I think 41 was the first paper. Basically, it's the sine qua non of measurement. If you're making a measurement, you must get a Gutman scale. Okay, now we can test the validity. What are the accuracy of the assumptions that went into the model? Well, we can do a mean square fit statistic for each person, and that tests the assumption that all the stochastic variance can be attributed to a single source in the case of a Roche model. So there's ENJX is the error. That's where the random variable variance comes from. And we'll take the mean square residual for each person. So we would start in the upper left corner, and you'd take the response and subtract from it the expected response, which would be in the other matrix, the corresponding cell in the neighboring matrix, and square it and average over all items for that person. And that gives you a mean square residual for that person. And you divide that. Remember, we have a model now that has a specific distribution built in. We divide that by the model's predicted variance for each person. And that is called a information-weighted mean square fit statistic, or the INFIT for short. And the equation below it is just putting in more attractive notation what it says in words above it. And so we have the actual observations, which are on the left. We have the expectations, which are on the right, which are generated by the model after we've done the maximum likelihood estimation. And we produce a ratio of the mean square difference, the mean square residual, to the expected variance, to predicted variance. And since we're using Gaussian distribution for the error, we expect this to be distributed, these residuals to be distributed as chi-square over its degrees of freedom. That's just a property of this equation. And what's shown on the left, the histogram, are the distributions of those information-weighted mean squares. And the curve drawn through those data are the predicted chi-square distribution. Curves on the right are the same thing, except those are cumulative distributions instead of the density functions. And I guess we could quibble over the little departure in one part, but for the most part, that's a pretty good fit. So just as a side note, doesn't necessarily mean you go start chopping off items because they're in the tail of the distribution. If the distribution fits, then it's meeting expectations of the model. It's consistent with the expectations of the model. If you get outliers or get multi-modes or the distribution's just the wrong shape, which often occurs, then that's evidence you've got a problem. Go one step further, we can ask, the assumption is all The variance should be the real variance in the distribution due to differences between people, and the rest of the variance should just be random noise. And so when we do a principal component analysis on the residuals, we find, first of all, the measure itself, the person measure, explains about 67% of the variance in this data set. And then doing principal component analysis on the residuals, we find the rest of it's down in the scree, that it's just random errors, the rest of it. So this particular instrument, the VF14, given to a group of patients, population of patients who have visual impairments, works very well. It's a very good measure. Okay, now what about intervention? What's actually happening? Well, one thing that can happen as a result of intervention is we can change the person measure. Okay, so the person measure at time t0, which would be baseline, gets changed by some amount. Delta, the Greek letter delta, means change. So this is just change in the person measure. So it goes from the baseline value to the baseline value plus or minus some change. We could get a change, and the delta in this case is just the difference between the person measure at follow-up and the person measure at baseline. We could also get a change in the item measure. Okay, notation's the same. We have an item measure for item J at time t0 baseline, and then we could change it up or down. So the change here is just the difference between those two. Another thing that could happen is the patient is playing two roles. They are the object of the measurement. That's what we want to measure, but they are also functioning as observers. Okay, they're making judgments and reporting results. Okay, in some cases, if the therapist is making the judgment, the therapist is the observer, and so it'd be the same equation, but just different interpretation of parameters. So in that case, the criteria, the response criteria at baseline, have built into them the person's bias. Okay, we normally don't express the bias separately, but the bias might change as a result of the intervention. Patient might be Hawthorne effect, the placebo effects, that these not necessarily real changes in the person or the item, but just the way the person uses the response scale, and they're more positive or overestimating their abilities, something of that sort. So we represent bias with the letter B, subscripted for that particular person. Okay, and B can be thought of as the average change in all the category thresholds across all the categories. Okay, so now, if we want to talk about the change in functional reserve, the way we'd set up the theory is to, the way we did it before, we substitute the difference between people, we just put the term functional reserve in, and we have other terms. But now we're going to add possible things that could change to this equation. B is the bias term, that could change. The delta P could be a change in the person measure, or delta I could be a change in the item measure for that person, so we're indexing it in. Okay, and we can take the B out of this equation here and subtract B from everything, and it'll show up here. So we can put all the terms that could be the outcome, we just make that part of, add that to functional reserve. Okay, and we could summarize those change scores, those change terms, with a single change in functional reserve, delta R and J, where that is just the combination of the terms that we collapsed into that. Okay, just a repeat of that last step. Now, what we want to look at is what is kind of the average change in functional reserve, because when we do outcome measures, we want a single variable. We don't want to have a vector of variables that we're now saying treatment A is better than treatment B because these 20 variables changed and more than these did. I mean, it'd be a very difficult thing to sort out. So we want to talk about a single outcome measure. So what we end up doing is averaging these changes across all the items for each person. And what you can see is if you average the person measures across items, the change in person measures will stay the same. That won't, the average across items is the same as what it was. If you average the bias, that doesn't change across items. But if we average the item changes across items, we get this delta I sub n, which is an average of that and specific to that person. Okay, now what we would normally do is calibrate the instrument. You've heard a lot about that today, calibrating instruments and creating item banks and so on. So we'd anchor the item measures and we'd anchor the response category thresholds to their baseline values for the population that you want to study. Okay, so what happens is that we can rewrite this equation for the average change in functional reserve to just a change in the person measure. Because if we're anchoring the values, by definition, there can be no change in the item. And by definition, we're not singling out bias. So what happens is that all changes in functional reserve, which is what causes them to change their response to an item, okay, that's what it's linked to, the data you're collecting, we're going to assign to the person measure. We're going to say it has been a change in the person measure. Okay, so like we just said, the item measure at time t is defined to be the same as the one at baseline, so that has to be 0. And the category threshold time t is defined to be the same as one at baseline, so the bias term has to be 0. So everything else so all of those changes, if they're really occurring, we're forcing them to show up in the person measured change. And we're defining the person measured change just as the change in functional reserve, which is what is being judged when the patient gives their response. Okay, so to demonstrate this, I'm going to do a simulation. So we'll take 500 people, made-up people, live in the computer. We have 19 items, which also live in the computer. This is very generic, not even talking about what we're talking about. Okay, and we'll have 4 response categories. Okay, and we took the baseline person measure and say it's normally distributed. It has a mean of 0 logits and standard deviation of 2.5 logits. And the item measures range from minus 4.5 to 4.5 in equal steps of 0.5 logits. And the category thresholds are minus 2, 0, and 2 for the 4 categories. Okay, 3 category thresholds if you have 4 categories. Okay. First category is anything less than C1. Second category is between C1 and C2. Third category is between C2 and C3. Fourth category is anything greater than C3. Okay, and we assume that the errors are normally distributed around a mean of 0. And just a little technical thing, we make the standard deviation pi over the square root of 3 because we're using what's called a logistic distribution. And that allows us to normalize the distribution for a logistic to be able to represent a normal distribution with a logistic. And we assume there's no correlations in this matrix of errors. In other words, ENJX, it varies as a function of person, it varies as a function of item, it varies across categories, and none of those things are correlated with each other. They're all independent. That's what's called local independence, which is what all these models use. Okay, and then we have our magic equation at the bottom for baseline responses, and that's how we generate the predictions. We grab a person, go right through all 500 people. We have a person measure for each one with a normal distribution. We plug in the person measure, plug in the item measure, take the difference, take the category thresholds, add a random draw from this normal distribution of category of errors, and add them to the category thresholds, and then ask, is it greater than 1, 2, 3, so on, and we define a response for that person judging that item in the computer. And the graph on the left shows the item measures that are estimated by win steps using a Roche model, Andrich rating scale model, versus the item measures we plugged into our computer to start with. And you can see a pretty good agreement. And on the right is comparing the person measures for all 500 simulated people, estimated by the win steps to the Andrews rating scale model versus the person measure we put in the computer. And the diagonal lines in both cases are the identity lines. So it's a line of slope 1, standard deviation, or intercept of 0. Okay, now we put a delta P in there. And we say there's going to be a change in the person measure by 2 logits. And this will change, we'll say it would change everybody's person measure by 2 logits. The treatment has one effect, it changes you by 2 logits. Okay, and so we put that in, so we increase every person measure by 2 logits. We run it through the computer again, through win steps, and we compare the item measures. We're not anchoring anything now. We compare the item measures we estimate from delta P up by 2 to what we estimated at baseline, and the graph on the left shows the relationship between those two. Perfect agreement between item measures. So incrementing delta P didn't do anything to the item measures. Okay, but person measures all went up by 2 logits. So they're on a line that has a slope of 1 but an intercept of 2. Went up but 2 logits above the other line. Okay, now let's write the equation with the bias term and the category thresholds, and we'll set the bias term as a change in 2 logits for everybody. And when we run that, same thing. On the left, the items don't change, but on the right, what we get is person measures fall down by 2 logits. So bias term acts the same way delta P does. Change in person measure or change in bias can't be discriminated. They act the same way. Now let's change 8 of the items and leave, out of the 19 items, we're going to change 8 of them by 2 logits. We're going to decrease their difficulty by 2 logits. And we're going to, the other 11 items we're not going to do anything to. We'll keep them the same. And you may ask, how is it we could change an item? How you might change an item. In my field, you're asking all these questions about activities you can do. We tackle them activity at a time. Can't read a newspaper, we provide you with a magnifier. You might be able to read the newspaper, you can't read anything else with it. So that magnifier is just targeted to that one thing. Anytime you're treating a symptom, that's one of your items. When you set goals, like in goal attainment scaling, you're treating things to achieve those goals, and you're ignoring other things. They're not changing. Okay, so your items, you can end up getting item-specific changes in your outcomes as a result of targeted interventions, whether you're working towards goals or working toward interventions that are very task-specific, and like accommodations or assistive equipment, things like that. Okay, so now when we compare baseline item measures to post-intervention item measures, we find that 11 items look a little bit above the line, 8 of the items that decreased by 2 logits look a little bit below the line, but actually what's happening here is that when WinSteps calculates item measures, it takes the average of all the items and calls that 0. Okay, so when it does that, then you end up straddling the line rather than the items you didn't change being on the line, okay, because the average changed. Okay, but what we'll see here is after doing that, we get a change in the person measure. Okay, there's this very small change in the person measure, but it's reliable. It's about 9/10 of a logit. And that's the dotted line that goes through the data. Okay, now what's interesting is if you remove the 11 items that didn't change, and we only leave the 8 items in did when we run it through WinSteps. We delete the items that didn't change. Then we see the person measures actually go up more. And what we're doing here is we're taking one additional step. We're anchoring the item measures to the baseline values, which is what often is done when you're looking at outcome studies. And we're anchoring the category thresholds to the baseline values. And so the black dots are the person measures with all 19 items in there, but all the measures anchored. The open circles are the person measures with only the 8 items that changed, and the other 11 items being deleted, still using the same anchoring. So you're seeing a change in the person measure. Okay, well, if we go back to our average change in item measures with this concept of average functional reserve, what we find out is if we're going over J items, and J in this case if it were 19, all 19 items, we can think of J as made up of two numbers. U is the unresponsive items, so there are 11 of those. K is the responsive items. There are 8 of those, and we're summing over just taking the average here over just the K items that are responsive. Now that's legitimate because delta I is 0 for the ones that are unresponsive, so if you include them in the average or don't include them in the average, you get the same average. But what you'll notice, the dots on the graph, is the average change in the person measure from this as we add more unresponsive items. So the first dot, we don't have any unresponsive items. That's just the 8 that responded. Second dot is that we have, I think, 2 unresponsive items included, just chosen at random. The fourth one is, or the third dot is 4 unresponsive, and so on. And you can see that steady drop in the person measure as you include more unresponsive items in with the items that changed. And the curve drawn through the data is from this equation. So it's just simply person measure drops as you increase the denominator. Okay, I'm going to leave time for questions, so rather than go through the next hour of the material, let me see what the next slide is. Well, let's just summarize it. So in my field, how you might change a person measure is remove a cataract. How you might change an item measure is provide them with a specific magnifier. And if the change in the item measure is not 0, that indicates intervention-specific differential item functioning. Usually diff is considered bad, but in our case, diff is an indicator of a positive outcome. And same with goal attainment scaling. It's an indicator of a positive outcome. So you want diff, but you got to be able to manage it and understand what's going on. So if you use a fixed item questionnaire, you might have a lot of items in there that you don't address. And if you're targeting items with your setting them up as goals, you may be diluting your effect by including unresponsive items. Just to show you that it's real, that this comes out, we did a clinical trial with it's called the Low Vision Intervention Trial in the VA at the Hines and Salisbury VAs. And they're legally blind veterans that participated. And the treatment group got the full bore low vision rehabilitation with assistive devices and everything else they need. And the control group got called every now and then and asked, how you doing? They were actually on the wait list to get into the blind rehab center, which gave us at least a year to finish what we were doing before they got their appointment to get in. And and we used a 48 fixed item questionnaire. And one thing with the VA BRC is that it's kind of a one-size-fits-all program. If you've never cooked in your life, you have no interest in cooking, by the time you get out of the blind rehab center, you'll be the cook in the family. So fixed item questionnaire is kind of appropriate for the VA, and this one was tailored to the VA program. And the person measures are estimated from Roche analysis by anchoring the items, as we talked about before. And this is the outcome in terms of person measure estimates. The blue is the baseline distribution of baseline values before rehabilitation for the treatment group, and the red is the distribution baseline of follow-up values, post-rehabilitation values for that same group of patients. And I don't have a graph of the control group, but they didn't change. Okay, but I'll show you that in a minute on some other things. That was for reading. The one I just showed you is for reading measures, and this is for mobility. So the effect was a little smaller for the treatment effect was smaller for mobility. But now, what we've done, because we've anchored the items, we've forced all effects of rehabilitation to manifest as a change in the person measure. Okay, and the question is then, is there evidence of intervention-specific diff? And so what we're looking at here is relative to baseline calibrations. What is the differential item functioning at the follow-up for the control group and for the treatment group? And what we're seeing is that each point is a different item, not in any particular order, and that the red shows no change in items over time, but the black is showing you that there are bigger changes for some items than for others. And that's for the reading items, and this is for the mobility items, same story. So we are getting evidence of differential item function. And so we can calculate what the change in functional reserve was on average for this group, and it was about 3 logits. And using the diff analysis, we can estimate what the average diff was, and it's about 1 logit, that it got easier, which means that the underlying person measure, what's common to all the items, not necessarily, I mean, it might have all been diff, but if they all fall by 2 logits, which is the delta P here, by at least 2 logits, we would assign that to the person because we have no way of sorting out which is item, which is person. And then when we subtract that, you notice the last item goes up to baseline, and what's left over is the diff relative to that item. So we end up with this effect. Okay, so let me just finish by saying that the way we have to modify the gas is to take into consideration, first of all, we have to anchor our items. So we really should work from an item bank. We're not a matter of working from a floating origin. That these goals, if there's a standard set of goals in your field, that these goals should all be calibrated, and which most likely would be items. And that whether we have the therapist do the rating or the patient do the rating or some combination of the two are doing ratings, and we're estimating parameters from that. Work in, but the idea is to judge the outcome based on the treatment. So if a patient says an item's not important, or it's not applicable, or it's not difficult, that you're not going to address it with your therapy. That to keep it in the assessment can only lower the effect. So then anchoring items to the baseline values of what's left. And really, the question would be, for goal attainment scaling, you only want to assess those items that represent goals. Now, there are exceptions to that if you're not doing goal-targeted interventions, but you're doing, if I change one thing, it's going to change their lives all the way across the board, then, you know, I won't quarrel with those people. But for a lot of rehab, we're very much oriented towards very specific targets. And then our tools, and then bottom line, it doesn't make a great deal of difference which of these many models you use. They all pretty much produce the same answers within tolerance, but there are theoretical considerations on all of these things, and I would urge you all to kind of get down in the weeds with the rest of us and learn about what your computer program's doing when it's estimating these parameters, because a lot of assumptions are being made that we're not even talking about at these meetings. And if you knew what they were, you would probably throw up your hands and say, why am I doing this? So be cautious in terms of the models you're using, it's important, I think the next step in the development of the field is to understand these models and to understand, make sure that the models represent what you believe to be going on and they represent what you're trying to do. You're not simply generating numbers and wondering why you're getting all this variability. So I thank you very much for your attention and take questions. I think the one thing I would add, there are two things I'd like to add to what you said. One is that most scientists are kids, and so kind of go back to being that skeptical kid. You know, when somebody tells you about their great models, it's probably wrong. All models are wrong, and so find out what's wrong with it. And don't be satisfied until you do find out what's wrong with it. All these models are very absolute in their assumptions. And it's kind of like, what are you willing to accept? What's the most reasonable? So you want to, at the very least, understand the assumptions. You don't necessarily have to get down and do the computations, but understand what assumptions are going into these models, and do they fit your situation? Like the graded response model is based on a physics model. Okay, so if you are, the graded response model has a very strong assumption in it, and that strong assumption is that the category thresholds are fixed. They do not vary between people. Okay, do you believe that? If you don't, why are you using it? Okay, Roche model has a very strong assumption. It says all variability comes in through the category thresholds, that there is no variability in the item interpretation. Okay, item interpretation variability introduces correlations that the Roche model can't live with. Okay, if you say, well, that's fine, that's probably the major source of variability between people, then use the Roche model. Okay, other models, each model, as it adds more and more parameters, can explain more and more things. So if you see a model laden with parameters coming in, and some of the models we heard today do a very good job of fitting the data at hand, but they become sample specific. They end up explaining what you, or simulating what you have, not really necessarily explaining anything, but you know, and you end up with a parallel kind of description of what the equations are doing to create this model. I keep doing that. I guess it's to wake you up. That's a flag that you should be skeptical about. Why do you need so many parameters in order to explain what's going on?
Hi, I'm Jeff Golson. I'm from UT Austin, and I've certainly learned a lot about this today, but I'm certainly still a novice. And perhaps I'm trying to map this too directly onto treatment intervention, but you had mentioned that if you delete the items that that no change was found, that the person functionality increased. Does that mean that zero change was found, or that you included the items that even of moderate change was there, and was it just measured at the pre and post, or is there a time variable in there to maybe allow for change over a certain point?
Well, it depends on what you're trying to assess. If what you want to know is where is this person in relation to where they were at baseline, then you maybe want to leave the items in. On the other hand, if what you want to know is what did my treatment do relative to the goals I set? Okay, well, if you have someone who comes in that has fairly modest goals, that there's, you know, that most things are okay, but there's just a couple things you got to fix, you could hit a home run, but all those other items that don't change because they weren't difficult to begin with, they will kind of wash out your effect. You're not going to see much of an effect. And if you're designing a big, expensive clinical trial to look for this, and you know, you're going to find that it's going to be down in the noise. On the other hand, you can make what relatively trivial changes. You know, there are 100 things they should be able to do, and you're only going to work on 2 of them, and so you throw out 98 of them. You could have a huge effect and just exaggerate the magnitude of what you're doing. So So there's a certain amount of auditing that has to be done in terms of making it clear of what it is you're trying to describe, a change in what. And it's a complicated story, but, you know, and it lends itself to abuse and cherry picking and doing things to inflate the numbers once you understand how to do it. But probably better that you know, if you're doing it, know that what's happening, as opposed to just kind of going ahead and administering an instrument and then wondering why you're not seeing much of a change as a result of your treatment. And we've seen that in low vision. The LOVIT study is getting huge effects, 2-3 logits. And the rest of the world's getting effects on the size of 0.3 of a logit, presumably doing the same things, but using very different instruments, you know, not designed for the intervention and so on.
Thank you.
You know, it reminds me of you know, the many, many years we were trying to measure treatment outcomes using batteries, like aphasia batteries, and I think it's the similar case that, you know, when you're looking across so many measures, across so many domains, we've probably had a wonderfully rich history of underestimating treatment effects.
Could you say a few words about the implications of treatment-induced diff for computerized adaptive testing?
Yeah, another part of this paper, which is going to be coming out in, I forget the name of the journal, Statistical Methods for Medical Research or something like that. But it's looking at the effects of these assumptions on CAT. And CAT, remember, uses anchored items. Okay, so you calibrate all the items, they have fixed values. You calibrate the category thresholds, they all have fixed values. Now you're going through and estimating person measures on a person-by-person basis using these fixed items and an algorithm that chooses items based on your previous responses. Well, if the item changed, when you go back into the bank to pull out the next item, you're going on the basis of the item measure. You're not going on the basis of any other information except that how they responded to the one you just gave them. So as a result, you'll find yourself kind of seesawing, that you get into a hysteresis that it has trouble converging on a solution because you're pulling out items that might have changed. Maybe the next time you pull out an item it didn't change, so the items aren't where you thought they should be. And then what we found in simulations, and it depends on how many items you have that changed and in how many are in your pool and things like that, but in the simulations we found that it had trouble converging, then all of a sudden it would start to converge, but it would converge on the baseline value. So it would converge at no effect. And so to use CAT as an outcome measure, before you believe it, I think you have to say, is there differential item functioning as a result of my intervention? And you might want to take a look at that before you jump in and use a CAT. And CAT already knows that you shouldn't have diff in there because they correct for that when they know it's present. And, you know, in the PROMISE study, the diff is a big important issue. But usually the kind of diff they're looking for is things like gender or comorbidities or some other thing that may produce it.